Good morning, guys. Let's have some discussion on stress quadric, and this is actually applicable to how the stress uh, tensors are manifested in terms of a quadric surface. No, as far as the equation of the stress quadric uh, is concerned, it will yield to a manifestation on how the stresses, the elements of the stress tensor are represented on what you call a quadric surface. Okay, so a quadric surface is simply okay a uh, a representation of a curved surface, um, more or less viewed only on the positive octant on a three-dimensional space, such as this one drawn here. Okay, so this can be in the form of a quadric sphere or spheroid. Can also be a quadric representation of a cylindrical surface, etc., which is actually formed from the nature, no, of of the stress tensor. So it's simply a representation of how the stresses are distributed on the x, y, and z coordinates, or simply the spatial dimension. And we have two properties which actually helps us deal with the formulation of such equations and solutions to problems now involving here. The first property is all about how the quadric surface is derived, no, from the fact that if we let a Q be a point on the quadric surface. Let's say I now make use of this okay, this figure to represent, let's say, a point Q here, and let PQ, and my point P force is reckoned from the origin there. So again, this is simply my radius R upon which my point Q is measured directly from the origin P. Okay, and the normal to the stress at point P acting across the surface normal to PQ is actually inversely proportional to the square of the radius. So this is actually your property number one, or say theorem number one, that will give you the basis on how to formulate the equation for the quadric surface. Okay, so we have defined a unit normal vector now here. Okay, Ni, upon which, of course, your stress vector uh, sigma is based on. Okay, so if this is your traction vector sigma I, and this is the unit normal vector Ni, then we can come up with this uh, property or theorem that states that the normal stress at P acting across the normal, the surface, okay, normal to PQ, okay, is inversely proportional to the square of the radius. So if I have here a unit normal vector defined by a direction vector kasi. Okay? We can now simply uh, note that your R here is considered now as the basis for your direction vector basis of I. So if I want to make use of a unit normal vector, I simply divide the direction vector, okay, basis of I with the length R, then I have a unit normal vector. Okay, the unit normal vector is actually uh, of the same direction with that of the direction vector basis of I, because here it is stated that the normal stress at the point P acting across the surface normal to PQ is the same, okay, direction vector upon which your normal vector was derived from. Okay, so this is now another relationship that you have to take note of when dealing with uh, quadric stresses or stress quadrics in general. So for the stress vector formula, this was the one that we have used time and again, and this is again what you call the Cauchy stress vector or formula. So to find the normal component n, we simply multiply um, sigma I by ni. Okay, so if you want to make use of the component sigma n here, if this is your n unit vector, then simply your sigma I, you just take the projection, okay, and taking the projection is simply a dot product operation in vectors. So sigma I dot ni is simply equal to nj sigma ji, which comes from the Cauchy stress formula, multiplied by ni. Okay, and if I want to interchange, okay, these two here, interchange these two, so I just make use of a transposition of my ji to ij here, and taking note that nj and ni are I and j here for the n vector are simply uh, dummy indexes, so we can actually interchange them such that your equation will come up with this sigma ij ni nj, which if I introduce another direction vector here in the form of basis of I will now obtain a another form of the equation, and normal of force and equivalent to sigma ij basis of I over r dot basis of j over r. And if I let n be equivalent to a certain constant k squared all over r squared, then I say that k squared is simply sigma ij basis of I basis of j. So this is the basis for your formulation of what you call your stress quadric, which is represented by the quadric surface. So for property number 2, the stress vector sigma I at P acting across the area that is normal to PQ is parallel to the normal to the surface of the stress quadric at Q. Okay, so if the surface is perpendicular to n, then the n vector is actually parallel to the normal to PQ also, because PQ, okay, defines the shortest distance, or the perpendicular distance from the origin up to the point on the surface. And you can do property number 2 by using a del operator. Okay, a del operator, a del dot, let's say phi, is actually called a divergence operation. Okay, so when you say the divergence of phi, you simply get the del dot phi. Okay, so a del phi, so these are additional notes. Del phi is a gradient. A del dot phi is a divergence. Okay, and a del cross phi is a curl. So these are just terms used by in tensorial mathematics which describe behaviors of solids and fluids to represent the mathematical formulation of such. Okay, a gradient can be related to slope. Okay, energy gradient, hydraulic gradient. Divergence can be um, attributed to physically to a substitution or simply a contraction of two vectors, okay, to form a scalar, a simple scalar. And a curl has something to do with rotation, just like a permutation. It's something to do with the associations of your ijk in terms of your epsilon uh, tensor. Okay, so we will deal with the applications of this later. Now, so we're still on the process of just uh, customizing ourselves to such operations. Okay, but when I say del operator, I mean a dot product of the del operator with that of your function. Okay, so normally this is a function. It can be a scalar function, can be a vectorial function, depends upon the use of the function. In this case, since this collapses to a zero order tensor, this is just a scalar. Okay, ij and ij are simply uh, contracted, and therefore this is a scalar quantity, and this means that this is a scalar function. Okay, so if phi now is a scalar function, then if I take a partial derivative of phi with respect to the position, I convert it now into a vector. That's why here I have now a free index which converts it into a vector. That's why, because if this is a scalar, I cannot make a dot product, no? Cannot make a divergence out of it. So since divergence has something to do with the del operator, and the del operator is simply the partial derivative with respect to the position, let's say k, of a certain uh, function. No? Okay, sorry. This is just an operator, so there's no function involved yet, then this has a direction is okay. Okay, so if I make use of this del operator now, with this I just take the partial derivative with respect to a vector of position or a spatial dimension consists of k. Okay, I cannot write the partial derivative symbol in MathCAD. That's why I'm using only the ordinary derivative here. But this simply it's automatic that this is a partial derivative, since your phi value here is a scalar function of your position. So it's an xyz. So phi is a function of x, y, and z, or simply in this case, an epsilon 1, epsilon 2, and a cassis of 1, cassis of 2, and cassis of 3. Okay, so this is your phi. And therefore, if I make use of a derivative now, I convert this scalar function into a vectorial function. Hence, my resulting, okay, my resulting uh, uh, expression here must be a vector. It must have a direction, okay? So that's why this is now my final value. If I multiply sigma ij with this using property number 2, then I can simply take the derivative of a vector position with respect sorry, this is not x, but kasi symbol, no? So the derivative of cassis of I with cassis of k is an identity matrix. Okay, so still remember that uh, if I differentiate x1 with respect to x1 is equal to 1. Okay, if I differentiate x2 with respect to x2 is equal to 1 also, and so on and so forth, such that I will now create a diagonal matrix equivalent to this identity matrix. Okay, so take note of this, no? The derivative of xi with respect to xj, or whatever variable you're using, in this case it's kasi, is simply equal to delta ij. And also, this is the derivative of cassis of j with cassis of k. This is a delta jk. And then I retain the cassis of j there and the cassis of I here. I now make these two equations. And taking note that this equation here, ik when merged into a sigma ij will contract into a sigma jk here. Hence, this becomes a sigma jk cassis of j plus sigma ik cassis of I. And look at the choice of the subscript. I have here a k value, I have here a k value here. Okay, and I are dummy repeated indexes, and these are j and j are dummy repeated indexes, meaning to say that I have to be consistent only in k. Therefore, this subscript jj and I can be collapsed into a single subscript, which is simply what? Okay, which is simply sigma. Okay, uh, I use a jk here, cassis of j. So I can collapse this into a sigma. My I can collapse into j also. Okay, and so this must be sigma j. Okay, so these two are symmetric. It can be a sigma kj, sigma jk, doesn't matter. What is important is these are of common terms, then I can add them, no, in order for me to get a value of 2 here. Okay, so I just change the index I to j and it will yield to these two. And take note that again, this is a direction vector divided by the magnitude uh, of that vector becomes a unit normal vector nj. And knowing that this is just related, we can convert the derivative or the partial derivative of your quadric surface phi with respect to k, or cassis of k is simply equal to 2r sigma k. Okay, why? Because this sigma jk nj is simply your Cauchy stress tensor. Okay, so your Cauchy stress is actually is a representation of your value for your stress tensor here. So this property may be used later to simplify the solutions to problems. Okay, so to highlight the use of property 1 first, we ought to solve this example 2.8, whereas to find the stress quadric at point 1, 2, 4, with the sigma ij tensor given in terms of this values and c is a constant. Okay, so your 1, 2, 4 here represents your vector of position in the y-axis. Okay, so this is yi equivalent to y1, y2, and y3. And these are simply 1, 2, and 4. So since there's no y3 involved here, we simply substitute 1 and 2. So minus c times 2 is, this becomes negative 2c. Okay, and c times y1 becomes c. And since this is symmetric, we know that always your sigma ij is symmetric. So don't forget about that. So this cy1 becomes c and cy2 becomes negative 2c. So knowing this matrix now here, we can now use property. This is property number 1 of your stress quadric. Okay, so we simply multiply. We can expand this using additional notation, but I have proven to you that matrix multiplication is better to use. Therefore, I just make use of a uh, dot product here. So converted into an epsilon, or sorry, a kasi sigma. Uh, this is actually kasi transpose. Okay. Or you can do a kasi transpose sigma kasi. So it doesn't matter. For as long as this is a row, and this is a column vector. Row vector, column vector. Sigma is at the middle. So if I do it, I just multiply this with this first. Okay. So if I do the simplification of this part here, I will get a minus 2c because of 1. Okay. And then comma. If I multiply this and this, I will get c 2c, it's consists of 3, I mean. And then c consists of 3. Okay? And then the last, I will get okay, comma, it's a minus 2c consists of 1. And then I will multiply it to consists of 1, consists of 2, consists of 3. I will get now what? This multiplied by this becomes minus 2c consists of 3, consists of 1, and then comma, c consists of 3, consists of 2, and then comma, minus 2c consists of 1, consists of 3, equals k squared. Okay? So this is minus 2, it becomes minus 4c consists of 3, consists of 1. Okay? So you can interchange this. And this is c consists of 3, consists of 2, or consists of 2, consists of 3. So the 2 here is actually one. Okay, so there's an error here, I think. So we'll double check it after this video. So why did this come up to have a 2 value here? Because I did this in MathCAD. But manually, this is the way on how to compute for it. Okay? Sorry, class. There's something wrong with this. The last, no? So this multiplied by this is, there's still an additional plus c cassis of 2. Okay, so I think that's the error there. So we have here a plus c cassis of 2. And then since this is on the a second, I have to multiply it on the second. Cassis of 2, cassis of 3. Okay, so that becomes 2. So it's already checked now, no? Because this is twice and this is 4 times. So this is now twice. So this final answer now is correct. So you have to know how to do it manually, and you also have to know how to do it in using a tool like a MathCAD, okay, for ease of computation. So thank you very much for listening. So I hope you know how to simplify this simple formulation on stress quadrics, which could be very useful and significant in your solution to continuum mechanics problem, especially on stress analysis. I'll see you on the next video.